In today's video, we're going to end our lessons on two population means, but today we're going to look at using the paired differences. Recall from the beginning of chapter 10, I talked about when we're dealing with two population means, we have either independent samples or dependent samples. So far, we've worked with just independent samples, where we looked at a pooled t-test or a non-pooled t-test. There's another test, the Mann-Whitney, that we do not cover in this particular class, but if we have data that is not normal, but is the same shape, we can use what's called a Mann-Whitney. Today we're going to focus on when is it important to use a paired t-test. So this is when you have, say, one individual. If you think of, for example, a drug trial or not even a drug trial, but if you were looking to improve your cholesterol level or something along those lines, and you decided to go on eating a healthy diet, you would record your cholesterol level prior to the diet and record it afterwards, but it has to be the same person, meaning it has to be paired information. You can't look at one person's cholesterol and compare it to someone else's after the diet because there has to be a baseline. And what we're looking at is what's occurring between the before and the after, what's occurring with those differences. All right, so the paired difference formula itself is probably one of the easiest and simplest hypothesis test statistic formulas that you're going to come across. Because what we really care about is our first variable is called our D bar. That is the actual differences. We're going to go through a set of data so you can see exactly what this D bar represents. It's the difference between if it were before and after, the before and the after. Then you have another new variable called S sub D. This is the standard deviation of those differences, where D bar is the mean of the differences. D bar is mean of the differences. And S sub D is your standard deviation of the differences. It's still very similar to an X bar. We're just going to call it a D bar. And S sub D is, again, standard deviation of differences. And like all of ours, we still need to divide by the square root of our sample size. Sample size has to be taken into consideration. So that's one of the main things that we're going to do. When we're setting up our hypothesis, the hypothesis is still very similar in that our null hypothesis is still comparing the mean of sample 1 with the mean of sample 2. And for that null hypothesis, we're going to just go with the assumption that they're equal to each other. The alternative is really going to depend on the question that you're being asked, right? What are we looking to test? Do we think mu1 is greater than mu2? Do we think mu1 is less than mu2? Or do we think they're just simply not equal to each other and we don't really care so much about less than or equal to? So your mean is going to set up very similar to what it did with your independent sample. So even though we're working with D bar, we're still comparing mean 1 to mean 2. So I think the best thing for us to do is really to kind of go through a problem and we can see not only how it's set up and what D bar and S sub D, what they actually represent, but you'll also let you know when it comes time for the test, what information I'll provide to you because, we only have so much time to take tests. All right, so I have a problem here. And this is taken from the textbook. You have this e-textbook in your in my stat lab, and this is on page 496 of that book. So here's the idea. We're going to look at cooling down with a cold drink. All right, before exercise in the heat is believed to help an athlete perform. So researchers actually conducted a study on this called the ice slurry ingestion increases running time in the heat. All right, so how did they come up with that? Well, they took a look at, what's the difference between cooling down with an ice slurry, which is like a slushy, which is basically ice, or just cold water. So that's what we're comparing. In order to do this comparison, you have to have the effects on the same individual. In other words, and this is exactly what they did if you read the rest of that paragraph. They took, they used only males in this case, and they looked at, what happened when they drank the slurry. Then they ran them through the same scenario with the same hot and humid environment, and then what happened when they drank just the cold water. And ultimately what they found was how much time in minutes it took to fatigue on the treadmill after they took the slurry drink, and then the same scenario after they had the cold water. So subject 1 took 52 minutes to fatigue with cold water, but it took 56 minutes with the ice slurry. All right, so subject 2 was 37:43. So you can kind of see it does appear that they are going a longer time. So, but again, like any other statistical analysis, does our data provide sufficient information? Is it enough to reach the conclusion we want to state? And what is that conclusion? Take a look at the bottom. At the 1% significance level, do the data provide sufficient evidence to conclude that on average, cold water is less effective than the ice slurry for optimizing athletic performance in the heat? So the mean standard deviation of the paired differences, the mean and the standard deviation is negative 5.9 minutes and 1.6. So here's what we need to do. You got to be really careful when setting this up, because is the cold water less effective? So this is mu1 and that is mu2. How do I know that? How do I know that's mu1 and mu2? Well, I can kind of get it with this idea that it kind of comes out negative, because to find d bar is going to be equal to mu1 minus mu2. It is super important in these problems that you define mean 1 and mean 2. And you set it up such as that. On the exam, I will define which ones mean, which is population 1 and which is population 2 to make it easier. So now, to find our set of differences, well, you got to do each one. So for this first one, I would take 52 minus 56, I get negative 4. 37 minus 4. And of course, that gives me negative 6. So what you need to do is kind of pause the video and just go through and find those differences. Keeping consistent, 1 minus 2, mu1 minus mu2. So those means are going to add up to negative 59. So they're the individual paired differences. Now, interestingly enough, and you can do this on your own if you like, if you found the mean of this entire set of data and found mean 2 of that entire set of data, okay, you can also get d bar. Or you can find d bar by using the sum of the differences, and d bar is going to be equal to the sum of those differences divided by n. In this case, negative 59 divided by 10, which gives us our negative 5.9. Either formula works. We're not going to take the time. And in fact, as you can see in this problem, it is simply given to us. I just wanted you to see where it came from. So you can actually take the mean of the entire set of data. If you have the graphing calculator, you can just plug it into the graphing calculator and get the mean, or you can open it up in StatCrunch and get the mean. Or find the differences and get the mean that way. To get the standard deviation, you would have to apply the standard deviation formula that you learned in chapter 3, I believe it was, back in stat 1, where you take each value, find the difference between that value and the mean. So each D value and the mean, square it, divide, sum them all up, divide by n minus 1 and take the square root. So you would just use your standard. But again, I will give that to you. Okay, so what we know so far is that our D bar is negative 5.9 and S sub D is given to us as 1.6. If you are asked in my stat lab to find it on your own, all you really need to do is open that set of data into StatCrunch and use the StatCrunch features to find the standard deviation, or to do the paired differences test, in which case your standard deviation will be given to you. The other piece of information, of course, we know is that n equals 10. Now, let's set up our hypotheses. As I had stated, the null is simply that they're equal to each other. In other words, it's the same amount of time, whether you drink the cold drink or the ice slushy, you're going to fatigue in the same amount of time. It doesn't matter. But let's take a look, and you've got to be really careful with reading this one, because it's not, if you see, you just need to be careful because it can be very deceiving how pair differences are set up. So in this case, is cold water is less effective than the ice slurry. So think about that a minute and tell me what you think the HA should be. This one, of course, is pretty straightforward. Mu sub 1 is less effective than mu sub 2. But again, you need to read it really carefully to ensure that the one that you think should be lower has the less than symbol pointing to it. Okay? Now, we take our formula. T equals D bar, negative 5.9, standard deviation, divided by square root of 10, and hit pause and calculate that. Sorry, I think there's a lawnmower in the background. I'm sitting outside, so I apologize for that. And it appears we get negative 9.82. Okay, we kind of expected this to happen because we could see by the data. Also, keep in mind, for some of these paired differences, you know, you'll get some negative numbers, some positive numbers. This one, everything did show a decrease, so we kind of expected this to happen. We can run a quick p-value approach for a right-tailed test. I'm sorry, left-tailed test. I don't know why I said right. Left-tailed test. If I put the negative 9.82 there, this would be my p-value. And you can go right to your t-table. So please take a look at your t-table. Okay. Of course, you're looking at degrees of freedom is just n minus 1, because again, we're focusing on just that one set of differences. So it's n minus 1. So you have degrees of freedom equaling 9. Look at 9. If you take 9, it is going to be way off the chart where the areas continue to get smaller. So your P is certainly smaller than 0.00. Sorry about that. 0.05. Since alpha is 0.01 according to this problem, we would clearly reject our null. This is a really small p-value. Don't forget that conclusion, which is so important. In this case, at the 1% significance level, the data do provide sufficient evidence. Sorry, it's really sloppy. Still sloppy. To conclude that cold water is less effective. Is less effective. Couple things you want to look for when you're doing this. You must include the significance level. If you are rejecting, then the data do provide. If you're not rejecting, then the data do not provide. And then context. Put it back in the context of the problem. You're basically rewriting that statement. Okay, hopefully that will help you. Again, on the problems you're going to do in my stat lab, I encourage you, usually in the upper corner of the data, there's these blue boxes. Click that and it'll open it in StatCrunch. On the test, as in this problem, I will certainly give you the differences. I will certainly give you the standard deviation. What you're going to have to do is really think about how the problem is written and think about that alternative hypothesis. But the formula itself is pretty straightforward once I give you that information. Okay? That's the end of this one.